You think a path is a line, a particle moves from here to there, it traces a trajectory, a smooth curve through space. Maybe it wiggles a little, but fundamentally it's a line, a path, something you could draw with a pencil. That's the picture in your head. That's what every physics diagram shows you. That's what your intuition screams. It's wrong, not a little bit wrong, fundamentally wrong. The kind of wrong that hides something so strange about quantum mechanics that most physicists don't even talk about it. They show you the equations, they wave their hands about all possible paths, and they let you keep your comfortable mental image of smooth trajectories connecting points in space. Richard Feynman gave us one of the most beautiful formulations of quantum mechanics ever devised. The path integral, sum over histories. A particle doesn't take one path from A to B, it takes all paths. Every possible route through space and time simultaneously. Brilliant, revolutionary, and almost universally misunderstood. Because when people hear all possible paths, they imagine smooth curves, lots of smooth curves, infinite smooth curves. They picture a particle exploring every gentle trajectory, every elegant arc, every well-behaved route from start to finish. That's not what happens. That's not what the mathematics says. And that's not what nature does. The typical path, Feynman's sum, isn't smooth at all. It's rough, infinitely rough. Rough at every scale you examine it. A path so jagged, so fractured, so fundamentally different from any curve you've ever drawn that it breaks everything you think you know about trajectories. Let me show you what Feynman's popular picture misses and why understanding roughness is the key to understanding what quantum paths actually are. Start with what Feynman actually said. In the 1940s, Feynman developed a completely new way to think about quantum mechanics. Instead of Schrödinger's waves or Heisenberg's matrices, he proposed something radical. A particle going from point A to point B doesn't choose one path. It explores all paths simultaneously. Every conceivable route weighted by a phase factor that depends on the action along that path. This is the path integral formulation. Sum over histories. To calculate the probability of a particle getting from A to B, you add up contributions from every possible trajectory connecting them. The paths that have similar phases reinforce each other. The paths with different phases cancel out. What survives is the classical path plus quantum corrections, beautiful mathematics, profound physics. It reproduces all the predictions of quantum mechanics while giving an entirely new perspective on what's happening. But here's the question nobody asks in the popular explanations. What do these paths actually look like? When you sum over all histories, what kinds of trajectories are you summing over? The standard presentation shows smooth curves, wavy lines that wander but remain fundamentally well behaved. The particle might take a longer route or a shorter route, might curve left or curve right, but each individual path looks like something you could draw. This is the trap. This is where intuition fails completely. The paths that dominate Feynman's sum are not smooth. They cannot be smooth. The mathematics forbids it. Let me explain why smooth paths are impossible in quantum mechanics. In classical physics, a particle follows a single trajectory determined by Newton's laws. That trajectory is smooth. It has a well-defined position and velocity at every instant. You can compute derivatives. You can draw tangent Dinge lines draws the path behaves itself, but quantum mechanics doesn't work that way. Heisenberg's uncertainty principle tells you that you cannot simultaneously know a particle's exact position and exact momentum. The more precisely you specify where the particle is, the less you know about where it's going. Now think about what that means for paths. A smooth path has a well-defined tangent at every point. That tangent tells you the direction of motion. It tells you at that instant exactly where the particle is going. It gives you the velocity. But velocity times mass is momentum. And the uncertainty principle says you cannot have exact position and exact momentum simultaneously. A smooth path violates quantum mechanics. If the path were smooth, if it had a definite tangent everywhere, you would know both where the particle is and what direction it's moving. That's forbidden. The mathematics won't allow it. The physics prevents it. So what kind of paths are allowed? What trajectories don't give you simultaneous position and momentum information? Rough paths, paths without tangents, paths that are continuous, connected, but infinitely jagged. Paths where no matter how closely you look, you cannot determine a direction of motion because the path keeps changing direction at every scale. This is what Feynman's path integral actually sums over, not smooth curves, fractal curves, nowhere differentiable trajectories, paths so rough that the concept of velocity becomes meaningless. And here's where my work becomes relevant. I spent my career studying roughness, not as a defect, not as noise to be smoothed away, roughness as geometry, roughness as structure, roughness as the fundamental character of natural phenomena. When I developed fractal geometry, I was trying to describe objects that classical mathematics couldn't handle. Coastlines that get longer as you measure them more finely. Mountains that stay rough no matter how closely you zoom in. Clouds with complexity at every scale. These objects share a property. They exhibit self-similarity. Not exact self-similarity where small parts are perfect copies of the whole, but near self-similarity where small parts have the same statistical character as large parts, the same roughness, the same type of irregularity, the same refusal to smooth out, and they have fractional dimension. A coastline is more than a one-dimensional line because it's so convoluted, but it's less than a two-dimensional surface because it doesn't cover area. It exists between dimensions. It has fractal dimension, a number that captures how it fills space across scales. Now, here's the connection to quantum mechanics. The typical path in Feynman's path integral is not just rough, it's fractal. It has all the properties I studied in coastlines and Brownian motion and natural phenomena. It's continuous, but nowhere differentiable. It has self-similar roughness at every scale. And it has a fractal dimension that tells you something fundamental about its geometry. The fractal dimension of a quantum path is 2. Let me explain what that means. A smooth line has dimension 1. It's one-dimensional, obviously. A surface has dimension 2. But a quantum path confined to moving through one-dimensional space has dimension 2. It's so rough, so convoluted, so infinitely wiggly that it partially fills a plane even though it's nominally a curve. This is extraordinary. A path through space that is geometrically more like a surface than a line. Not because it spreads out into 2 dimensions, but because its roughness makes it fill space more thoroughly than any smooth curve could. The key to understanding this is Brownian motion. In 1827, Robert Brown watched pollen grains dancing in water. They jittered constantly, moving randomly in every direction. This is Brownian motion, the random walk of particles buffeted by molecular collisions. Brownian motion produces paths, but what kind of paths? In 1905, Einstein analyzed Brownian motion mathematically. He derived how the particles diffuse, how their average displacement grows with time. But something else emerged from the mathematics. The paths themselves have strange properties. A Brownian path is continuous. The particle doesn't teleport. It moves smoothly from point to point in the sense that there are no gaps. But a Brownian path is nowhere differentiable. At every single point, the path has no tangent, no direction, no well-defined velocity. The particle is always changing direction, always jittering at every scale you examine. Zoom in on any section of a Brownian path. What do you see? More jittering, more roughness. The small section looks just as jagged. The jagged is the large section. The roughness doesn't smooth out. It persists at every magnification. This is self-similarity. The Brownian path has the same statistical character at every scale, and its fractal dimension is exactly 2. It wanders so thoroughly that it almost feels the plane. Now here's the profound connection. Feynman showed that the paths dominating his path, integral, have exactly the same mathematical properties as Brownian motion. They're continuous but nowhere differentiable. They have fractal dimension 2. They exhibit self-similar roughness at every scale. This is not an analogy. This is not a metaphor. The mathematics is identical. Quantum paths and Brownian paths share the same geometry. In fact, you can formulate quantum mechanics entirely in terms of Brownian motion. This is called the Feynman-style formula, a rigorous mathematical connection between quantum propagators and expectations over Brownian paths. The particle explores all possible Brownian trajectories weighted appropriately. The smooth curves in the textbook diagrams aren't just simplified illustrations. They are fundamentally wrong about the geometry. The real paths are rough, infinitely rough, fractal. So what does the popular picture miss? When people visualize Feynman's sum over histories, they imagine exploring smooth alternatives. The particle could go this gentle curve or that gentle curve. Maybe it loops around. Maybe it takes the long way. But each alternative is a well-behaved trajectory with a definite direction at each point. This mental model is completely incorrect. The paths being summed are not smooth alternatives. They're rough, they're fractal, they have no direction at any point. They fill space in ways smooth curves cannot. And here's why this matters. If you think about quantum paths as smooth trajectories, you miss the essential geometry. You miss why the uncertainty principle works. You miss why quantum mechanics is fundamentally different from classical mechanics. You miss the deep connection between quantum theory and the mathematics of roughness. The uncertainty principle isn't just a statement about measurement limitations. It's a statement about geometry. It says paths cannot be smooth. It says trajectories must be rough. It says the universe operates with fractal curves, not classical trajectories. This is what I mean when I talk about the geometry of roughness. Classical physics uses smooth shapes, smooth trajectories, smooth curves. Classical physics lives in the world of Euclidean geometry, where everything has tangents and derivatives and well-defined directions, but quantum physics doesn't live in that world. Quantum physics lives in a rougher world, A world where paths have no tangents, where trajectories have no velocity, where the geometry is fractal, not Euclidean. Understanding this doesn't change the predictions. Feynman's path integral gives the same answers, whether you visualize the paths correctly or not. The mathematics doesn't care about your mental images, but understanding changes your perspective. It shows you that quantum mechanics isn't just classical mechanics with some uncertainty sprinkled on top. It's a fundamentally different geometry, a geometry where roughness is basic, not exceptional, where smooth paths are forbidden, not merely improbable. And now let me be clear about what I'm not saying. I'm not saying Feynman was wrong. Feynman's mathematics is impeccable. The path integral formulation is one of the great achievements of theoretical physics. It works, it predicts, it unifies. What I'm saying is that the popular intuition built around Feynman's work is wrong. The simplified picture that people carry in their heads, the mental image of smooth curves being summed, that picture misses the essential geometry. And this is a recurring theme in my work. Over and over, I've found that nature is rougher than our intuitions assume. Coastlines are rougher than smooth curves. Mountains are rougher than simple shapes. Market fluctuations are rougher than Gaussian statistics predict. And quantum paths are rougher than smooth trajectories. The question isn't whether something is smooth or rough. The question is what kind of roughness. What scaling law does it follow? What fractal dimension does it have? How does the roughness behave across scales? For quantum paths, the answers are precise. Dimension 2, Brownian scaling, self-similar roughness at every level, the same mathematical structure as the random walks I studied in so many other contexts. This connects quantum mechanics to a much broader framework, the framework of scaling, the framework of self-similarity, the framework of fractal geometry. Quantum mechanics isn't an isolated mystery. It's part of a pattern where roughness appears fundamental, where smooth shapes are exceptions, where the real geometry of nature is fractal. This is why I spent my life developing tools for rough shapes, because rough shapes aren't pathological, they're typical, they're what nature actually produces. They're what the universe is made of at its deepest level. Smooth is the exception, rough is the rule. Here's what I want you to understand. When you hear about Feynman's path integral, when you learn about sum over histories, when you picture a particle exploring all possible routes from A to B, don't imagine smooth curves. Imagine roughness. Imagine fractals. Imagine paths so jagged that they have no direction anywhere. Paths so convoluted that they partially fill planes. Paths that look the same at every scale because they're self-similar. That's what quantum mechanics actually computes. That's what the mathematics describes. That's what nature does. Quantum mechanics didn't break reality. Your smooth intuition did. The universe isn't made of smooth trajectories disrupted by quantum uncertainty. The universe is made of rough trajectories, fractal trajectories, trajectories that never had smoothness to lose. Classical physics isn't the default with quantum corrections added on top. Roughness is the default. Classical smoothness is what emerges when you average over enough scale, when quantum effects wash out, when the fractal geometry blurs into apparent simplicity. at the deepest level, paths are rough, space-time is rough, the fabric of reality is rough. This is what fractal geometry teaches. This is what studying roughness reveals. This is why I spent decades developing mathematics for irregular shapes, because the irregular shapes aren't the exception, they're the reality. The smooth shapes we draw in textbooks, the elegant curves we imagine in our heads, those are the idealization. Those are the simplification. Those are the convenient fiction. Nature is not Euclidean. Nature is fractal. And understanding that changes everything about how you see the universe. The next time someone shows you Feynman's path, integral with smooth wavy lines connecting 2 points, remember what those lines really represent, not gentle alternatives to the classical path, fractal monsters, nowhere differentiable curves, Brownian trajectories with dimension 2. That's the geometry of quantum mechanics. That's what the mathematics actually describes. That's what Feynman's beautiful formulation is really computing. And that's what the popular picture completely misses. Not comfort, not smooth intuition. Truth.